word. I don't think you use it in daily life. But on the left here, you have Simone in a low energy conformation. It's still her. She's not a different person. And then on the right here, you've got Simone in a very high energy conformation. So a conformation is sort of, you know, it's the same molecule that we're going to be looking at, but it differs in three-dimensional space because rotation is possible about single bonds, right? The same way that humans can move their arms and legs around. Okay, so here's the word. And, you know, this definition might be hard to understand, but if you use the analogy, I think it's more helpful. Different arrangement of atoms that are interconverted by rotation about single bonds. So we're going to look at a molecule right now. And actually didn't build this particular one, but why don't I go ahead and do that? So I don't know if you guys can see this very well. But here's a molecule, and it's basically an ethane with an oxygen atom. So maybe it could be ethanol. But right now, the red dot just represents anything. And you can actually rotate about the carbon-hydrogen bonds. Each one of these bonds rotates, but it doesn't really change the conformation. But if you rotate around the carbon-carbon bond, you can see that you can get to all of these different structures, right? If you freeze them out, the same way you take a photo of a gymnast in midair. And so here is one conformation where the red atom is kind of in line with this carbon-hydrogen bond. And here's another conformation, right? And it looks different. The red atom is what's called, it's 180 degrees away, it's anti-periplanar. Okay, so two different conformations here that we're looking at. So just like people, one of these conformations will be higher in energy than the other. And that's the second topic that I really want you guys to master today, is the idea that there are these different energy conformations. And as a student of OChem, you will have the power to predict which one is more stable, which one is higher in energy, less favorable. Okay, so we're gonna take a look at this molecule again, and we're gonna do it in the context of just ethane. And so, again, really for this chapter, I can't emphasize enough how important it is to start playing with your model kits. I think the TA team, LA team, and I will all agree that we all used our model kits extensively, and we still do when we deal with more complex structures. And so either we use computational modeling or plastic models, but these are very useful tools for visualizing things. So another vocabulary word, make a flashcard, practice this word. This is called eclipsed conformation. In an eclipsed conformation, if you're playing with your methane, and if you're playing along with us today at home, what you're gonna do is you're gonna align all of the CH bonds. And so if I look at it from this point of view, it just looks like a Mercedes symbol, right? All the CH bonds are actually aligned perfectly in ethane. So this is one conformation, it's called eclipsed, right? Just the same way like in an eclipse when the sun, the earth, and the moon kind of align, right? This is the eclipsed conformation. In the second conformation, what you're gonna do is you're gonna take your ethane molecule and you're gonna rotate it by 60 degrees, either to the left or the right, doesn't matter. And you'll get to this type of shape. This is called the staggered conformation. In the staggered conformation, notice that the carbon in the front is bisected by the CH bond in the back, right? They're not aligned. And so this is the staggered conformation for an ethane molecule. There's a 60-degree angle difference here between these two CH bonds, the front one and the back one, whereas on the eclipse conformation, there's a 0-degree dihedral angle. Okay, so kind of take a moment, absorb those two definitions. You're gonna be asked, for example, on an exam, hey, which conformation is this, eclipsed or staggered?